In this next question, we have silver sulfate. This is about a sparingly soluble salt. So clearly speaking, they are going to ask you about KSP, which is equilibrium constant for a sparingly soluble salt. And they want you to state the units for one free, well actually it's not one free mark, it's just 1 mark. So pretty stingy here, this old paper. In the new paper, perhaps you get 1 mark for this and 1 mark for the unit. Anyway, so what you do first, you want to try and write an equation. So the solid dissolve in water, dissolve in solution to give you the ions. We get a silver plus aqueous ions and a sulfate aqueous ion. Every equation you write has to be balanced. So what we have there must be 2 Ag plus. Hang on, just give me a minute. Don't know why this thing doesn't move properly. So 2 Ag plus because I have 2 Ag plus there. 1 of the sulfate give you 1 of the sulfate. They want the KSP expression. So what I don't want to do is I don't want to write that as the KSP expression. We should write the proper answer in here. So what we get is we have what we have there will be concentration. Actually, there's no divide by anything because this is a solid on the right hand side. So we just have the, what I mean is you have a solid on the left hand side. So you're just going to write in the concentration of the aqueous ions on the right hand side. So 2 of that Ag plus, and therefore you raise the power in the stoichiometric equation for the concentration there in the KSP equation. So just like you would do for Kc expression as well as Kp expression back in AS chemistry. Here we have a concentration square and we have another concentration. So we're going to get a total of mole per dm cube square multiplied by mole per dm cube. You're going to get mole to the power of 3. And then dm minus 3 square is dm minus 6. And then you add it with minus 3. So minus 6 plus minus 3 is going to be minus 9. So you get that mole cube, dn minus 9, bookkeeping there. Based on this KSP equation there, so I can move my equation down there because I'm going to do some sort of equilibrium question now. Calculate the value for this KSP. So if you want the KSP expression, you need the concentration of Ag plus, and we have the concentration of its saturated solution. So this is like Ag2SO4 saturated solution. This is as much of it dissolved in water as possible. So if I have 1 mole of this that dissociate, it will give me 2 mole and 1 mole of that. So I only have 2.5 times 10 to the minus 2 that dissociate in there. So if that is 2.5 times 10 to the minus 2 mole per dm cube, so therefore this thing is this one. So 1 mole of this gives 2 mole of that. If this much dissolve in water in the saturated solution, therefore the concentration of Ag plus is going to be 2 times 2.5 times 10 to the minus 2. I get 5.0 times 10 to the minus 2 mole per dm cube. Now this one, 1 mole of these give you 1 mole of the sulfate. So the concentration of the sulfate is still 2.5 times 10 to the minus 2 mole per dm cube. They want us to calculate the value. So the KSP is just going to be put in the value carefully and use bracket. This is square for the concentration of the Ag plus, and this is multiplied by the 2.5 times 10 to the power minus 2. So key that into your calculator carefully. So 5 times 10 to the minus 2. So you will write in 5.0 and then exp minus 2 on your calculator. And you square that. You multiply by 2.5 times 10 to the minus 2. And altogether you get 6.25 times 10 to the power minus 5. Of course, you have the unit there previously, so I don't have to write it again. But in my final answer, I should always try to be as accurate as possible by including the unit that I did correctly from the previous part of the question there. What do they want here? They want to relate solubility to the lattice, the enthalpy change of solution, which is that thing there, as well as the enthalpy change of hydration. So if I have the solid there, the silver sulfate, the silver 1 sulfate, by the way, because it's very important to name with the Roman numeral for the oxidation number, because it's transition metal, they can have more than 1 oxidation number there. What is what? So they haven't labeled arrow there, but this is being formed from something. This is being formed from its gaseous ions, that is going to be lattice enthalpy or lattice energy. So I'm just going to write down the gaseous ion. Of course, you have 2 Ag plus, so I also have to balance my equation so that everything is correct there. I've done a mistake there. It shouldn't be aqueous. It has to be from its gaseous ions in order for you to define this as lattice correctly. So delta H, theta lattice, this is the lattice energy. Is the energy required? Well, actually not required. It's the enthalpy change. In fact, it's going to be exothermic because it's enthalpy change when you form 1 mole of the ionic solid from its gaseous ions. Now, how about solution and hydration? So these are gaseous ions. In order to relate to hydration, what you will get is you will get hydration and blah, 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 blah. We don't have that thing there, so we just need to label hydration. But actually, this thing is 2 times the hydration of Ag+. By right is 2 times the hydration of Ag+, because you are hydrating 2 mole of this gaseous ion, whereas hydration is for hydrating 1 mole of gaseous ion, surrounding it or reacting it in a large amount of water, get an infinitely dilute solution there. And this one is plus 1 times the hydration of the sulfate. Now, why do I write this here? Because the question did not specify hydration of cations or hydration of anion. They just said enthalpy change of hydration. Using this as an example, complete it relating these 3. So based on the question, we only given this value, this expression, not value. So I've just written down this expression, but I know this one here is represented by this whole thing there. Okay. And of course, the last thing, we have to write the arrow. The arrow is actually going downward because hydration of the cation, hydration of the anions, you are going to get 2 Ag plus aqueous plus SO4 2 minus aqueous like that. And this is the solid dissolving in a large amount of water to give you an infinitely dilute solution under standard conditions. That is going to be your enthalpy of solution there. Standard enthalpy change of solutions because it's under standard conditions, 298 Kelvin, 1 atm pressure. If you see this Hess cycle, Hess law says that enthalpy change of a reaction is independent. It does not depend on the route you take as long as you start from the same reactant and end out at the same product. So if I think about, I don't know, it doesn't matter which way around I think actually. If I just start from there, this direct route, so enthalpy of solution, there's the direct route. This is the indirect route. I'm going opposite, so it's going to be minus the lattice. And then I'm going the same way, so it's plus the hydration, which include the hydration of the cation as well as the hydration of the anion, as I've written down above. But since the question just said enthalpy of hydration in there, so I'm just going to put the enthalpy of hydration in there, and that's the 4 marks there in that question. Next way of this question, we have some electrochemistry. So on the right hand side, you will see you use a silver metal. So this is silver metal, the metal itself as the electrode. And why do we do that? Because we have Ag2SO4 aqueous, and this is not very soluble obviously. It's by saturated solution, so you get Ag2SO4. So this thing there, not very soluble. This is a bad electrolyte, because how are you going to get 1 mole per dm cube, 1.00 mole per dm cube? It's going to be almost impossible, especially when this thing is very sparingly soluble. That's why you did KSP just now, almost not soluble at all. On this side, you have platinum electrode, and you have a system where you have iron 3. So this is actually iron 3, because you have iron in the 3 plus oxidation number. It's iron 3 sulfate there. And then this bottom one is actually iron 2, because it's iron 2 plus, and then sulfate. So iron 3 versus iron 2. This is metal ion, and metal ion, as stated in the syllabus, you must use a platinum, which is an inert electrode, as you have a 1.00 mole per dm cube equimolar mixture of 1.00 mole per dm cube iron 3 plus, and also 1.00 mole per dm cube of iron 2 plus. Now we're going to use the data booklet. Of course, in the real 2022 exam onwards, the data booklet will be provided inside the question paper itself. So make sure you will choose the right one. This is the iron 3 plus, iron 2 plus redox system. For this system on the left hand side, it's metal ion and metal ions. So 3 plus going to 2 plus, this is plus 0.77 volt. And the other one there will be E naught Ag plus Ag. So alphabetical order, Ag should be easy to find. The first one there, so plus 0.80 volt. So looking at that, I should be able to see that this one is the more positive E naught compared to the iron 3, iron 2 system. So what can I do here? Let me see if I can move it around a little bit more. So 1, 2. Then what do I do next? I just need to find E cell. So E cell is going to be the E red minus the E ox. The more positive value is going to be the silver system. So that is plus 0.80 minus plus 0.77. What you're going to get is something positive because the more positive value favors reduction and the less positive value favor oxidation. So I get that as plus 0.03 volt. Calculator will not show you the plus, but E cell as stated in all the E naught values, sign, value, and unit, unless you're 0.00, which is not likely unless you have the standard hydrogen electrode. They are looking now for the positive electrode. If we think about the positive electrode, electrons come here. Electrons go to positive electrode. Be very careful. We are not doing electrolysis. We are doing a electrochemical cell system. So electrons are negatively charged. Electrons will flow towards the positive electrode. Now, which one is the E red? The E red is the more positive one. So this is E red. E red is where you gain electrons. You gain electrons at the E red. So electrons go to the E red. The E red is the Ag plus and Ag. So electrons go here. Electrons go here because it is reduction here. It's the E red. And if electrons come here, electrons are negatively charged. This makes the silver electrode as the positive electrode. So the answer there must be silver electrode because electrons come here and you lose the electrons from the ion 2, ion 3 system here. Okay. Now that was based on the E naught cell value. That was based on the value in the data booklet, assuming standard concentration. But this question now is asking you, how would the actual E cell vary, okay, compared to the E cell under standard condition? Explain your answer for just 1 mark. We can see that in this equilibrium, this thing is not going to be under standard conditions as this is sparingly soluble. So the Ag2, don't know why that is not writing properly. So the Ag2SO4 is very sparingly soluble. So if it's only very sparingly soluble, so not very soluble at all in water, its concentration, so Ag plus concentration falls way below, well below the standard conditions, well below the standard 1.00 mole per dm cube concentration. And if that is true, then what will happen to your reduction potential? Because you have Ag plus electrons going to Ag there, and this is your E naught of plus 0.80 volt. And remember that was your E red. That was what we said to be the E red. So if you are way below 1.00 mole per dm cube, this equilibrium will favor to the left hand side. To try and increase the concentration of Ag plus, this equilibrium will favor to the left hand side. And when you favor the left hand side, when you shift to the left hand side, this will become less positive because you favor to the left hand side. Then the E red, which is the Ag plus and Ag, would be less positive. So if the E red become less positive, as if this is not very close to zero now, if this thing become less positive, that means this is going to become less positive, this is going to become more negative or less positive, meaning the whole reaction is going to become less feasible. So day 1 on the E cell, I've only talked about E red, so therefore the E cell, which is no longer standard, so no longer standard because you fall below the standard concentration, that will become less positive. So less positive, or you can say more negative. It's really up to interpretation there. Both will be acceptable and both will be correct as well. Okay. Now the next bit of this question, how would the E cell change if you add a little bit of concentrated Na2SO4? What does the Na2SO4 actually do? Let me just work out what is happening here. Something is wrong with my pencil actually. How would the E cell change if you add a little bit of concentrated sodium sulfate? We know that all sodium salts are soluble. If all sodium salts are soluble, we are going to get an increase in the sulfate concentration because this is a common ion with this KSP equilibrium. Since we get more SO4 2- in the equilibrium, you can imagine the KSP equilibrium set up earlier in the question. If we have more SO4 2- from the sodium sulfate, this equilibrium will try to remove the SO4 2- from the equilibrium. It will shift to the left-hand side. When you shift to the left-hand side, you will get even lesser Ag plus concentration. You get even lesser Ag plus concentration as a result of this common ion there. They are just asking for how it would change. They don't ask for explanation. Actually, they do they? Actually, they might later on, but anyway. So when that happened, we get the common ion effect. And what is the common ion effect? It basically means that more Ag2SO4 precipitate out. And if that precipitate out more, your Ag plus aqueous is going to decrease. And when your Ag plus aqueous concentration decreases, this equilibrium for the Ag plus Ag is going to favor to the left even more. This is going to drop lower than 0.80. It's going to become less positive than 0.80. So how would the E cell change? Well, the thing that contains the Ag2SO4, how would the E cell change? If I add it to the Ag2SO4 there, the E cell would behave the same as here just now, because here my Ag plus concentration drops. Here my Ag plus concentration drops, so this equilibrium will shift to the left. This will become less positive, so the E red become less positive. Less positive minus the same value, your E cell will become less positive. So E cell becomes less positive, or if you want, you can say more negative. That would be okay as well. Alright, so how about if I add it onto the other one, Fe3 plus and Fe2 plus. The sodium salt is soluble, so the iron 3 and the iron 2 are completely soluble. That's why here you have aqueous solution and aqueous solution. So adding sodium sulfate there is not going to change anything. It's not going to precipitate them out because they are not in equilibrium. They are completely soluble. So there should be no effect on the concentration of the iron 2 and iron 3 at all, as these are solution and these are not KSP equilibrium. So no effect on the E cell, because there will be no effect on the E-ox whatsoever, because these things are already soluble. Okay, now explain any changes you have stated. They just want the any changes. We don't need to talk about the no effect. We need to talk about this thing here. So we can talk about the common ion effect. So Na2SO4 is a soluble salt. As the concentration of sulfate increases, what's going to happen is more Ag2SO4 precipitates out. And if more Ag2SO4 precipitate out, this is actually the common ion effect. It is not going to be relevant by you stating the effect without explaining it. It's not going to get you the marks. So more Ag2SO4 precipitate out, Ag plus concentration decreases. So the E-ox, not the E-ox, the E-red, which is for the Ag plus and Ag, just like how we explained for the previous bit of the question, this thing is going to shift to the left in order to try and increase the concentration of Ag plus. Le Chatelier principle, counteract the change to try and increase the concentration of Ag plus, shift to the left, this one become less positive. So if the E red Ag plus Ag becomes less positive, so what will happen to the E cell then? The E cell will become less positive. Okay, so hopefully that makes sense to you. They're pretty stingy back then with just 1 mark for this long explanation here. Okay, the new syllabus, however, will probably ask you in terms of Nernst equation. So be aware that there is something called Nernst equation, which is to do with calculation of the electrode potential, of the cell potential, when you are no longer under standard conditions. So non-standard conditions, what is going to be your E cell, your cell potential there. That is part of the new syllabus from 2016 onwards. What do we have in this next question? This is the last bit of this long question. We are having a weak acid. So we have equilibrium there, weak acid. We are given some Ka value there. So we know that for a weak acid, Ka is H plus, and then the conjugate base over the Hx. These are all concentration at equilibrium. We also know that these are 1-to-1 ratio, the conjugate base and the weak acid H plus. So this is going to be approximated. You can approximate that to H plus square, and then you can approximate the bottom to the initial concentration of the acid, since very little of it dissociate when you are a weak acid. So what we have there really is we want the pH. So I can work out H plus is going to be the square root of Ka multiplied by Hx initial there. So subbing in the value, so 8.9 times 10 to the minus 4 times the initial concentration, which is 0.1 mole per dm cube. Don't forget to square root your final answer. So when I square root my final answer, I get 9.43398 times 10 to the minus 3. But what do I want? I want pH. pH is minus log 10 of H plus. So from my previous answer, I take the log 10 and then take the negative log 10 of it. I get 2.025. Looking at the value here, this is one significant figure, 0.1 mole per dm cube. Looking at the Ka, this is 1 and 2 significant figure. I would probably give these to 2 significant figure just to be appropriate with the data given in the question for this calculation. That's the end of this 13-mark question there. In this question number 5, we have atoms and ions, and we are talking about 3 subatomic particles, protons, electrons, and neutrons. And if we have this number on top, that is called the mass number. That is also known as the nucleon number. It's to do with the number of protons plus the number of neutrons, protons and neutrons in the nucleus of an atom. So carbon has 6 protons. That is the proton or the atomic number. So what we have there will be 6 protons. We have a 2 minus charge there. So that's because we have gained 2 electrons. There's 8 electrons. We have 14 minus 6, which is 8 neutrons there for this isotope of carbon 14 there. In terms of this next part of the question, I don't think you need to relate, you need to learn about them. They are from the old syllabus prior to 2016. This was the group 14 chemistry that they would have learned previously. But the CCl4 is basically inert to hydrolysis, as the CCl bond is the longest out of the 3. It's the shortest out of the 3 actually, because of the small size of carbon. So if it is the shortest, something is definitely wrong with this thing here today. It's the shortest bond out of CCl versus GeCl versus the SnCl. And therefore it is the strongest bond, and therefore not easily hydrolyzed, not easily broken or hydrolyzed. Okay, but as for the rest of it, I don't think we need to talk too much about that. That was basically the reason for the reactivity. This is in the AS bonding 2022 syllabus, where they will expect you to relate bond energy, covalent bond strength with bond length. This is to do with the size of your atom, and then you can relate to reactivity. If you need to break the bond, are you breaking a stronger bond or are you breaking a weaker bond? All right. As for this chemistry, this is actually quite a useful A2 electrochemistry question. So what you need to do is we need to know that Cl2 is an oxidizing agent. So that's straight from your AS chemistry of halogens. So when that is true, if we look at the E0 value from the data booklet, so what does the Cl2 give me? Cl2 plus 2 electrons, that one is plus 1.36 volt. Should probably write better then, plus 1.36 volt. And then you are trying to use this as an oxidizing agent. So you're oxidizing the SN2 plus to SN4 plus. So we're looking at the SN4 plus on the left hand side, because everything in the data booklet, the E naught value shows you reduction potential. So we have E naught. Okay, I gotta fix this thing now. Okay, E naught, SN4 plus and SN2 plus, and that give me plus 0.15 volt, whereas the E naught PB4 plus and PB2 plus, that give me plus 1.69 volt. So we are saying that there is a reaction between SN2 plus and Cl2. So if we have a reaction between SN2 plus and Cl2, what we're gonna get will be the Cl minus and the SN4 plus. So SN4 plus there, so 2 Cl minus, that will lose 2 electrons, and this will lose 2 electrons, and this will gain the 2 electrons. So this is the balance equation, and what you have there is your E cell, which is your E red minus your E ox. And if that is true, the Cl2 goes to Cl minus. This is going to be your E red, and this is going to be your E ox. So you can see that something which is more positive minus something which is less positive, you're going to get something positive. 1.36 minus 0.15. Your calculator show you 1.21, but you need to know electrochemistry must have sign, must have value, and must have unit. And you can relate this to the new syllabus. The new syllabus say delta G equal to minus NF E cell. And if the E cell is greater than 0, so the delta G is going to be lesser than 0. So what we can say is spontaneous and also feasible reactions related to delta G there. But an aqueous solution of PbCl2 does not react. So now we are onto the negative bit now. So if we react, if Cl2 oxidizes Pb2 plus to Pb4 plus, we need to show the E cell is going to be the E red, which is the Cl2 acting as oxidizing agent, so they will undergo reduction. So the E red is plus 1.36 from the chlorine, and then that is minus plus 1.69. As you could see, something smaller minus something bigger, that is going to be negative, and your calculator will show you something negative. So your delta G there, which is minus NF E cell. So N is the number of electron transfer, which is 2 electrons. F is a positive Faraday constant. Minus and the minus will give you positive. So delta G will be greater than 0. This is not feasible, not spontaneous. Answer the first bit, answer the second bit, write an equation for this reaction, which we already did, and that's the end of that 3 marks. Kind of a good electrochemistry question, although it's more related to all the syllabus on the group 14 chemistry there. Now this next bit of the question is definitely just electrochemistry, so this will be relevant to the current syllabus as well. What is the relationship? You just need to state it. So this is F equal to the Avogadro constant multiplied by the electronic charge, which is the charge for 1 electron. Faraday constant has a unit of 96,500 is the value. The unit is coulomb per mole. This is the charge. Is the charge for 1 mole of electrons. It's a charge for 1 mole of electrons. If you have the charge for 1 electrons, you multiply by 1 mole of electron, you're going to get the charge for 1 mole of electron. That's basically what it means there. Now when you pass a current of 1.2 ampere and you pass it over 30 minutes into dilute sulfuric acid, we are going to do an electrolysis of dilute sulfuric acid straight from your O level or IGCSE level chemistry. You have the sulfuric acid, which give you H plus, SO4 2 minus, H plus and OH minus. So the H plus is just going to, dissociate one of them. And when I say dissociate, what I mean is discharge. Discharge at the cathode, that's the right word. Between the hydroxide and the sulfate is the hydroxide that's going to get discharged. So the H plus the 2 electrons that will go to the H2. This will happen at the cathode. Reduction happen at cathode for your electrolysis. As for your OH minus, the OH minus will become O2 and H2O and electrons, and you balance the equation with 4 OH minus and 2 H2O and 4 electrons there. So you know that is your oxidation at the anode there. Oxidation at the anode because reduction happened at the cathode. Overall, what you're gonna get is you're gonna get the H2O getting electrolyzed, the H2O getting electrolyzed to give you hydrogen at the cathode and oxygen at the anode there. And you're going to have H2SO4 remaining, and in fact they're going to become more and more concentrated as these electrolysis continue there. So what do we get? Blah blah blah. This is the reaction that happens at the anode because this is oxidation. So this is an alternative equation which you can write. You know, it's pretty much the same thing as that. It's just the water dissociating in solution to give you the O2 and the water there. And the OH minus come from the water. So essentially you're still losing electrons there, and you will still get the completely balanced equations even if you write this, or this would be pretty much the same there. But what do they want here? They want you to calculate a value for Avogadro constant. They're trying to guide you. There are 5 things to be calculated there, and there are 4 marks to run up these 15 marks questions. So let's try to do them one by one. First of all, calculate the number of mole of oxygen produced. So let me just number these stuff that they want us to calculate. So number 1, the number of moles of oxygen produced. Oxygen is a gas, and I get 130 cm cubed there. So this is the gas volume, and this has to be divided by 24,000. Oh, this is frustrating. Something is definitely wrong with this thing here. So 130 divided by 24,000, and this is cm cube, and this is cm cube per mole. We know that in the periodic table at the bottom, it's given as 24.0 dn cube per mole. Here's 24,000 cm cube per mole because it's in cm cube there. So we want to calculate, so we want to give a value. So, you know, calculate and put it into a calculator. 130 divided by 24,000. I get 5.417 times 10 to the minus 3 mole. I don't want to run up too early, so I just leave it as 4 significant figure for the time being. That should be enough. Now, what is the number of mole of electrons? Well, from the equation, 4 mole of electrons react with, well, is produced along with 1 mole of oxygen. So I will relate the mole of electrons to the oxygen. 4 mole of electrons, 4 mole of electrons is to 1 mole of oxygen, is to 1 mole of oxygen. So what is my actual mole of electrons? Is to the 5.17 times 10 to the minus 3 mole of the oxygen. So students who are used to my channel, you know that this is the usual method I like to use when I talk about, this is really frustrating actually, when I talk about my mole ratio. So actual number of mole of electrons is going to be 4 times that answer from the previous bit. 5.417, 5.41, I can't even press my calculator correctly. Times 10 to the minus 3 times 4. So this one will give you 0.021668 mole. 21668 mole, okay, never mind. So now I need to find the number of coulomb pass. This depends on the question. So you pass 1.2 amperes over 30 minutes. So we know Q equal to IT, I there, and then the T has to be in seconds. So it's 1.2 times 30 times 60. So Q is equal to IT. That was 1.2 amperes. And multiplied by 30 minutes, converted into 60 seconds. Well, converted into seconds by multiplying by 60. So 1.2 times 30 times 60, I get 2160 coulomb. So this much mole of electrons is for 2160 coulomb altogether. What's the next thing that they want? The number of electrons pass. The number of electron pass. If you look at the data booklet, of course, you'll be given this data in the question for the new syllabus, obviously. So we know that this charge, 2160 coulomb, is for 0.021668 mole of electrons. What are we trying to find actually? We want to find the number of electrons, that are passed. We know that the charge of 1 electron stated in the data booklet will be 1.60 times 10 to the minus 19 coulomb. So I guess if that is for that, we want to find the mole of electrons, right? We want to find the mole of electrons. So what do we want? We want the number. We want the number of electrons passed. This is for one electron, and we have this much charge. This is for one electrons. I think I've gotten this the other way around. So, 2160. Nope, that doesn't make sense. 1.60 times 10 to the minus 19 coulomb is for one electron. So 2160 coulomb is for how many electrons? Yeah, that seems to be the right way around. For direct proportion. So you have greater number of charge. That means you must have greater number of electrons like that. So 2160 divided by 1.6 times 10 to the minus 19. I get 1.35 times 10 to the 22 electrons. This is the number of electrons. Number of electrons. Last but not least, what do I need to do? I need to get the number of electrons in 1 mole of electrons. So we know that this is the mole of electrons, and this is the number of electrons. So the relationship between Avogadro constant and this actual mole of electrons is going to be the charge for 1 mole of electrons. The charge for 1 mole of electrons. What am I doing actually? We want the number of electrons passed. So we did. We want the number of electrons in 1 mole of electrons. The number of electrons in 1 mole of electrons. So the number of electrons is equal to Avogadro's number multiplied by the mole of electrons. If we want the Avogadro's constant, now what do they want? They want the number of electrons passed. That one should be okay. The number of electrons passed. The number of electrons in 1 mole. The number of electrons in 1 mole is Avogadro constant. So that is the number of electrons divided by the mole of electrons. That is the number of electrons, which is 1.35 times 10 to the 22 divided by the number of mole of electron from the previous bit of the question earlier. And this should give you your Avogadro constant divided by that. And I get 6.23 times 10 to the 23, and this is to 3 significant figure. It is the number of electrons in 1 mole of electrons. Okay, so that's the end of that 4-mark questions, and that concludes that 15 marks question overall.